Welcome back, students, to this afternoon session of the fifth day of the school. We have Professor Badri Krishnan continuing with his second lecture on theoretical aspects of black hole physics. He'll be speaking to us today on quasi-local black hole horizons. Over to you, Badri.
Okay, thank you, Sriram. So I'll continue from yesterday. And so this is the plan for today's talk. So I ended last time by discussing oscillator horizons, and I'll continue that today. I'll review some of the concepts in the beginning. And then, in fact, all of today's lecture will be dealing with oscillator horizons. So the goal will be to derive the laws of black hole mechanics for you. And in doing so, we'll need notions from what is known as symplectic geometry, and I'll try to be brief in that part. Then I'll conclude by talking about higher multiple moments of oscillator horizons. So in the next lecture, we'll change gears quite a bit, and we'll go to dynamical situations, and we'll talk about dynamical horizons and results from numerical simulations. Okay. So, but today will be oscillator horizons. So let me start. So as we discussed towards the end last time, so the interesting case here, so which is in fact very useful and is valid for 99.99% of the time for any black hole, is that you have a black hole itself in equilibrium, which means that there is no infalling matter radiation. So for all intents and purposes, there is the black hole area and its mass and is all a constant. The space-time itself is allowed to be dynamical, so there is no global stationary killing vector field. So in fact, the universe itself could be expanding, could be doing what it wants, but the black hole itself is isolated. And so now I'll repeat some of the stuff from yesterday. So we shall introduce now a series of definitions with increasingly stronger conditions. And again, the goal is to derive for you a lot of laws of black hole mechanics. And this will be a very different derivation from what you saw in Eric Gorgolon's lectures. That is the conventional derivation, what he did. So you have an expression for the mass, you have notions of its gravity, you have notions of angular momentum, and I'll mention some of these later. And then you take, you vary them and you obtain then the laws of the first law of black hole mechanics. Here we shall do it in a very, very different way. Okay. So I'll talk about that in this talk. So these are some references, and most of this talk is based on these two papers. Okay, so the starting point for us is what is called a non-expanding horizon. So again, as I said, we want to extract the minimum amount of conditions that allows us to prove interesting results and to show the laws of black hole mechanics. So we'll need essentially two definitions in this talk. And the third one, which I will mention, but we will not really use. The first one is the simplest one. So this is the minimum you can expect an isolated black hole horizon to satisfy. So first of all, we need this two topology S2 cross R. So again, S2 is a space-like direction and R is a null direction. So therefore, there's a usual projection operator we can construct in this case. So I just take S2 cross R, drop the R part, and then I get a spherical manifold there. And that projected spherical manifold will have a Riemannian metric with the usual properties of a spherical topology. So the important point is that the S2 cross R, the R direction is meant to be null. So we have these preferred curves, the integral curves of the null generators of the horizon, which are meant to be null. And this means that if you embed this delta, this manifold delta in a space-time, then of course you can project the space-time metric onto this manifold, but this projected metric is then null, which means that it has one degenerate direction and two space-like directions. So which means that you cannot, you can invert the metric, but the inverse of the metric is not unique. And it also means, as we'll discuss that in a minute, which is that this metric by itself does not uniquely determine a connection. So now the other condition is that the expansion of these null normals to this delta should vanish. So this, as we saw, the expansion is a key thing, which tells you about the rate of area increase. And we require that this should be 0. And finally, we shall require that the field equations hold at the surface, and that the stress energy tensor is such that we have this energy condition. So if you're confused by this energy condition, you should just note that if you contract, for example, TAB times LB, this contraction here with, let's say, L once again, so you have TAB LALB. So of course, if this is future causal, then you can show that the result must mean that this TAB times LALB must be positive. So this is just the energy condition that we shall need, but this is a minimum that we require here. Okay. So again, any questions on this definition?
Please raise your hand or leave a message on chat if you have any questions. I don't see any at this stage, but
okay, good. So I hope everything is clear on this point. So let's proceed.
Can I ask a question?
Yes, of course.
Now, can I, when you define this theta L for these null normals, can I create a picture of, are these, the fact that it is 0, does it imply these light rays will remain parallel or converge? What does that imply?
They'll remain parallel. So they never, so no, they cannot converge. So they'll remain parallel. So the expansion is really 0, right? So if they would converge, then the expansion would go to, minus infinity. So that doesn't happen.
I understand. Thank you.
So yeah, so the picture you should have in mind is of a cylindrical manifold of topology S2 cross R, and which has this parallel light rays going along it. Okay. So in fact, let me just draw that on the blackboard here. So just so that it's an important question. So I think you should keep this picture in mind. So you have then okay, so these are the null normals, the integral curves of that. Can you see the screen? Then you see the blackboard, by the way. Okay, so I hope that was somewhat visible. So
we are not able to see it very clearly. Maybe you need to tilt it a little.
oh, I see. Okay, so let me in fact make it a bit.
That's better. Yeah.
Okay. So it's really a very simple picture. So imagine a cylindrical, I can't draw 3 dimensions here. So it's a cylindrical thing. And you have null rays ruling this cylinder. Okay.
Yeah, there is another question. Sumit, unmute and speak.
So am I audible, sir?
Yes.
Yes.
Okay. Sir, can you please just explain again the fact, like you said, that on the non-expanding horizon, you don't have a unique connection. I mean, the non-expanding horizon being a degenerate surface, how are we able to invert? Because the metric, the determinant of the metric should be 0. So inversion of the metric to find the connection should not be possible over there.
Exactly. So that's what I'm going to say. So in fact, that was second point here. So, which is that on a manifold, I mean, as you have learned in your GR course, if you're given the metric, there's a unique Levi-Civita connection connected to that, right? That is the expression for the Christoffel symbols in terms of first derivatives of the metric. So that if you go to the derivation, at some point you have to invert the metric to get the Christoffel symbols. And in this case, since the metric is not invertible, all the components of the Christoffel symbol are not determined by the metric. So there is some free information in the geometry which is not contained in just this degenerate metric on the horizon. Okay, so that is entirely true. However, what the nice thing that happens for a non-expanding horizon is that, first of all, I should say that, in fact, even if you were to start off with the space-time connection, which is this covariant derivative here, if you were to sort of restrict that its action onto vector fields tangent to the horizon, then the result is not guaranteed to be tangent to the horizon still, right? So, and then it turns out that in fact, in general, it's not that trivial to do this pullback in a well-defined way. However, for a non-expanding horizon, because of this vanishing expansion condition, so you can show in fact that the projection or the pullback of this space-time connection does give an intrinsic connection, which we'll call D here when restricted to the horizon. So in fact, there is a well-defined connection on the horizon, D, except that it is not determined fully by the degenerate metric on the horizon. Okay? So in other words, there's the free geometric information on the horizon is the two metric, the degenerate three metric Q, and this connection D. Okay, so did that answer your question? So I mean, you're completely right.
I get it. Thank you.
Okay.
Thank you.
The other interesting information is that the area of any complete cross-section of this manifold is the same. So we'll call it A. So any oscillator horizon, any non-expanding horizon has uniquely determined an area to it. Okay. So this means that no matter how you slice the horizon, so you could take, so let me just again draw this here. So you could take any slice like this, or you could be any sort of highly distorted slice as you wish. The area of all of these will be the same. Okay, and this again is something very hard to visualize because, of course, in such a cylinder, right? I mean, if it's a space-like cylinder, then you can distort any cross-section of it and make its area arbitrarily large, right? But you cannot do that for a non-expanding horizon. Okay. So now let's derive some more interesting properties. So the first thing is that, of course, this horizon is a smooth manifold, so its null normal must be integrable. It's a smooth surface, so that means that the null normal must be surface orthogonal. Okay. So that means that its twist must vanish. So now we shall apply this and use the Ray-Chaudhuri equation. So let me just remind you unfortunately, I have it on the older slide. So give me just a minute. I'll just stop sharing and then I'll share the other screen. Okay, so just give me a minute. So let me just share. I just want to show the Ray-Chaudhuri equation again. So this is Ray-Chaudhuri equation. This is what we discussed last time, and this is what you must have also learned about from Eric Gurgulan's lectures. So that if I have the expansion, the rate of change of the expansion is given by this equation here. So as we said before, so each term in this expansion, except for this omega, is negative. So the twist vanishes, so that means that theta dot is guaranteed to be negative. So now we require that in fact the theta must exactly vanish, right? So theta dot is vanishing and theta square of course also vanishes. So that means that in fact that sigma square plus this, I can just take out the negative signs then, so then it means that sigma square, twice of sigma square, plus this 8 TAB LALB, there's some 8 pi G factors here, sorry I missed that. Anyway, it doesn't matter, the point is that it is positive. So two positive terms is 0, that means each of these terms must vanish independently, right? So that means that the shear must vanish, sigma must vanish, and also this component of the stress energy tensor must vanish on the horizon. Okay. So with this, then let me go back to the to today's slides. Okay, so this is what I said. So then we have already from the Ray-Choudhury equation for non-expanding horizon, since expansion vanishes, then of course the shear must also vanish. And this component of the stretch energy tensor must also vanish. Okay. And you can go a bit further, in fact. You can also show that, in fact, not just this RAB, but also any contraction of this R with any angular vector, right? So if I take n to be any vector which is not just along the null direction, but also, let's say, could be a space-like direction. So it could be any angular vector. So this must also then vanish. Okay. And then, as I said before, yeah, this already said, so that for non-expanding horizon, we do have an intrinsic connection on it, which is this D, but this is not determined by the metric. Okay, so I hope that the basic geometrical structure of a non-expanding horizon is clear for now. So next we'll define a very important one form, which is called omega. So that is defined in the following way. First of all, you can show that from the expansion free and the shear free condition, so this derivative grad A LB, if I contract that with any vector that is tangent to the horizon, then the result can be written in this form. So I can define a one from omega such that this condition is true. Okay. So in other words, it means that if you are confused by this, so just drop the x's out and imagine that the index A is always pulled back to the horizon. So it's always, components are always tangent to the horizon. So then this combination grad A LB must be given by omega A times LB, where omega A is one form intrinsic to the horizon. Okay. And I told you already that I could scale the null normal by any function f, which is positive and non-vanishing. Well, if you do that, then you can just plug in a different f times L here. So the omega transforms in this way. So this omega goes as omega plus dA of ln f. Okay. So in fact, this omega has a very special interpretation. So it is a part of the connection on the horizon. So it's a connection on the, so along, if you like, the normal direction, right? So along the L direction. So any derivatives of L is given to you by omega. So angular derivatives are determined by the metric because on the angular direction, the metric is non-degenerate. So this is the part of the connection that is not determined by the metric, in fact. Okay. So that's an important point, and we'll use this omega quite often in the rest of this lecture. So now let us derive some more interesting geometric results here. So to do this, let us introduce what is called a null tetrad on at the horizon. So that means I choose a basis at the horizon, which is consisting of two null normals L and N, and a complex vector M. Okay. So the combination of L and M and its complex conjugate is meant to be a null tetrad, which means I can expand any vector as a combination of these guys. And I require that this null tetrad satisfies the condition that if I take L dot N, I should get -1. If I take M, sorry, it should be M inner product with M bar, that should be +1. And all other inner products should vanish. Okay. So that is a null tetrad, and this is what is used to decompose the Weil tensor. And for us, the two important components are psi0 and this should be a psi1. So that is psi0. So that is this combination here with C being the Weil tensor, and I have this sort of contraction of the elements of the null tetrad that gives psi0. And I have one more contraction here in which I have L, M, L, and N. So that should be psi1, so that's a typo. So both of these vanish, and this can be shown. I won't derive the whole thing here, but it turns out that both of these have to vanish. Okay. So as I said, even though we made such a simple definition of a non-expanding horizon, the consequences are pretty important. So it leads to a lot more results than you might have imagined, I think. So, and then the other thing is that the quantity psi2, which is another component of the wild tensor, but it's not M&M, but it's M&M bar, okay? So that appears in psi2. So that in fact is gauge invariant. So it means that I can, of course, there's not a unique null tetrad at the horizon. I just require that the L must be tangent to the horizon. Apart from that, any other choice is allowed, okay? So any other choice that you make of the null tetra, I can change, I can keep L fixed. I can scale it by a function. I can change N, M, M bar such that I preserve this inner product. So with any, so these essentially, I can make any Lorentz transformation of this null tetrad, preserving the direction of L. All of these are allowed null tetrads, right? And for all of these, psi2 will be the same. So a specific component of the wild tensor psi2 that is singled out to be completely gauge invariant. Okay, and in fact, its imaginary part is the curvature of this connection omega. So if you take the imaginary part of psi2, that gives you, with some prefactors, the curl of this one form. Okay. And the real part of psi2 turns out to be the scalar curvature of the horizon. So if you take the metric on the horizon, on the spatial metric, the Riemannian part of it, and you compute its scalar curvature, so that is given by the real part of psi2. Okay. So let me just interpret this. So the vanishing of psi naught says, in fact, that there is no infalling transverse radiation into the horizon. However, psi3 and psi4, so in this formalism, the wild tensor has the wild tensor has 10 independent components, and these are captured in these 5 complex combinations. So we show that psi0 and psi1 vanish, psi2 is gauge invariant, and psi3 and psi4, in fact, do not need to vanish. So this shows, in fact, that this is a very general construction here. So even though there is no infalling radiation at the horizon, there can be horizon that is sort of going along the horizon, not infalling, but going sort of, if you wish, transverse to it. Okay. So thus we can have radiation in the spacetime that is non-vanishing even at the horizon, if you wish, but there is no restriction on the rest of spacetime. So what you end up with here is really a very general surface in which you have singled out just the minimal features that you need. That it is time independent in terms of no infalling radiation, but the space-time itself can have radiations, can be dynamical and can be radiative, except that the radiation cannot fall into the black hole horizon. Okay. So the details of all of these statements, I mean, we can, you'll find in the references that I gave you, and it'll take me too long to arrive it here, but I hope that at least the idea is clear, right? I mean, if not, then there's a good time to ask questions.
Are there any questions, Stuart? Yes, there is a hand raised. Sumit, unmute and speak, please.
Am I audible, sir?
Yes.
Sir, can you please just go back to the definition of omega?
Yeah.
I mean, here can we, I mean, is it allowed to interpret omega as the eigenspectra of this derivative operator? I mean, this covariant derivative operator?
Well, I mean,
because you said that
it
XA is common on both sides. So, I mean, after all, is it?
Yeah, so the X is just meant to indicate that I'm only allowed to now act on this. I'm only allowed to differentiate any vector tangent to the horizon. Okay, I cannot take derivatives off the horizon. So that's the only purpose of X here. So indeed, so if you wish to sort of rephrase this in terms of the D, this dA, so you'll get the D of LB is omega A times LB. So in that sense, yes. So it preserves the direction of L, if you wish. That's what.
So these omega A's are basically one forms on the cotangent space of this this isolated horizon.
Exactly. Yes.
Okay. Thank you, sir.
Are there any other questions? I don't see anything else, Badri.
Okay. Thank you. Yes, omega is really a connection, right? So this transformation law should remind you of a gauge transformation of a connection. Okay, so in that, so it's really a connection on the, if you like, the normal bundle to this non-expanding horizon. Okay, so now, so I hope that this part was clear, that non-expanding horizon. So now let us strengthen this condition a little bit more. So in fact, we shall need this strengthening when we want to show black hole mechanics. So the next step is what is called a Wiki oscillator horizon. So this is a non-expanding horizon. So now remember that for non-expanding horizon, I could have chosen any null normal that I wished, right? So I could take a null normal L, scale it by a function, and get a new null normal that is completely fine, as long as that function was non-vanishing and always positive. So I preserve them that all the L's are feature directed, and this is completely fine. So you can do that, and all the results I told you will completely still be valid. But now let us restrict ourselves to a choice of null normals, which can only be rescaled by a constant, not a function. Okay. If you do this, then the omega itself is invariant. So if you go back now to how omega scales, omega changes. So omega changes by the derivative of the logarithm of that function. If I'm only allowed to scale by constant, then the omega is invariant under those gauge transformations. So once you do this restriction on what L's are allowed on the permissible class of L's, then omega becomes invariant. So therefore, I can talk about the omega for a Wiki oscillator horizon. And then I require, in fact, that this omega should be time independent. So if I take the lead derivative of omega along the L direction, I should get 0. Okay. So this is requiring that this part of the connection is time independent at the horizon. And as we shall see, the time part of this omega is surface gravity, and we can already see that here. So if you go back now to the definition here, so if I take x to be L, so I have that LA grad A LB is L contract with omega times L, right? So the contraction of L with omega is the acceleration of the null normal. So that is the surface gravity. Okay. The angular parts of this connection omega encapsulate angular momentum, and I'll talk about that in detail later in this talk. And also it contains the higher multiple moments of the horizon. So I'll discuss that also in the rest of this talk. So now you might say, well, this seems all very abstract. How does this really help us in any way? So the first thing is that the zeroth law is now easy to show. The zeroth law says that the surface gravity should be a constant. How do we show that? So let's do this little, apply this identity here. So the lead derivative of omega is L contracted with the exterior derivative of omega plus the derivative of L contracted with omega. Okay, so this is the surface gravity, L contracted with omega. So now this derivative d omega, the exterior derivative, that we already showed. I'm not sure, I stated it, but it's not so difficult to prove, in fact. So that this derivative here is given by the imaginary part of psi 2, and there is this volume element here, which is the 2 volume element on the horizon. So this is only angular. This is the angular volume element on the horizon. So if for a Schwarzschild black hole, this 2 epsilon just means sine theta d theta d phi, okay, written as a 2 form. So the contraction of this with the null direction is 0. So this is purely angular. So in fact, it follows with all of the previous machinery that in fact, this vanishes. So therefore, the surface gravity must be a constant. Okay, so this is the zeroth law. So this tells you that to have the zeroth law, you require not a non-expanding horizon, but you require a stronger condition, which is this Wiki oscillator horizon. But you still have now the freedom on which class of null normals you choose, right? I said that I have to restrict myself from the full allowed range of L's to a given equivalence class, within which I can scale by a constant. Okay, and this is not this is not unique. So I can take different in this very general setting. I can take a different class of null normals. I'll get a different surface gravity. Okay, and we'll discuss this later. But also, I should mention here that all of this argument can be extended to include matter fields. So, for example, if you wish to include electromagnetic fields, so then by the same argument, you can show that in fact that the potential will have to be constant on the horizon. So that is then the analog of the zeroth law for electromagnetic fields. Okay. Is this part clear? Any good time to stop for questions?
Any questions, students? There is Sumit with another question. Sumit, go ahead.
Sir, I mean, for the proof of this zeroth law, is it entirely geometrical? I mean, I fail to see like where is the dynamical content of the theory getting inside the proof? Because I mean, is there any input of the matter fields or something into this proof for the zeroth law?
Yeah, the matter fields are fully included. So of course, as I said, I've only discussed this for the vacuum case, but you can include matter fields and everything goes through. So it's because of the energy conditions, right? So, so that requires the specific matter components to vanish at the horizon.
Okay.
So it's really very general. So you can include Yang-Mills field if you like. You can include electromagnetic fields, and the zeroth law is this derivation holds.
There is another question. Yeah, sorry.
Yes, go ahead.
There is another question which asks, can you explain why LA omega A leads to surface gravity?
Oh, okay. So again, so there's different ways to define surface gravity. This is a very natural one in this context. So as I said, so this X can be any vector tangent to the horizon. So in particular, I could take this X to be L. So then look at the left-hand side here. That is LA grad A of LB. And that is simply the acceleration of L. And this is again in Eric Gorgon's lecture, probably one of the ways to define surface gravity, which is the acceleration of the null normal to the horizon. So what you do, in fact, more naturally in let's say for a Schwarzschild black hole, is that you take the time translation vector field, right? So you take this T, and that becomes null at the horizon. And again, the acceleration of that vector field is what gives you the surface gravity. So it is what acceleration an observer must have so that he doesn't fall into the black hole, it stays on the horizon. Right? And so if I take LA grad A LB, then I get this contraction of L with omega multiplied by L, right? So that's why this is the acceleration. So the acceleration is proportional to L, and the pre-vector is the surface gravity.
So there is another question. Guillaume, please unmute and speak. Guillaume, we are not able to hear you.
Can you hear me now?
Yes, we can hear you now.
Okay. So my question was about the condition on the Lie derivative along L of omega. I would like, because you gave a mathematical justification somehow, but I would like to know if there was a physical motivation. Of course, I understand that this leads to a constant surface gravity, and maybe this was one physical motivation, but is there something deeper? And I would like to understand the philosophy behind this definition of weakly isolated horizon somehow.
Right. So the motivation was coming from killing horizons, if you wish. So in the killing horizon, what happens is that a lot more is required, right? So you require not just these specific components of the connection to be time independent, but everything is time independent in that case. So what we wanted to do here was to extract from the killing horizon the minimal conditions that you need so that black hole mechanics is still valid. So that's why we started off with a non-expanding horizon. So there, we didn't require this condition. So we could scale our null normal by any function as we wished, as I said. But now that is not enough, right? So that doesn't lead to black hole mechanics. So as we shall see, you cannot show the first law of black hole mechanics with that condition. You need something more, but we don't want to go all the way to a killing horizon. We require all the components of the connection to be time independent. So we require the least amount, right? We're still keeping sort of the horizon being isolated and being time independent, but the philosophy here is to really require the least so that you can prove black hole mechanics, or to see what is it that the minimum that we can impose and still show black hole mechanics. Did that answer your question, Guillaume?
Yes, thanks.
Okay, good. So so this is in fact goes into the next, which I won't discuss here. This is a large topic by itself. So on a weakly oscillator horizon, we only require this omega to be preserved, okay? But in fact, you can go further. You can say, well, why just omega? Why not all the components of the connection? And in fact, that is what is called an oscillator horizon in the end. So just to give you an idea here, so still it is the case that with this condition on omega, it does not single out any cross section of the horizon. There's no way you can single any specific cross section out, okay? To do that, in fact, if you wish to do that, for example, so that would, for example, tell you what the rest frame of the horizon is. So to do that, in fact, it can be done. For that, you need to require, in fact, that all the full connection has to be time independent. Okay. I will not discuss it further here, so we can discuss it sort of in discussions, but I will not sort of talk about this further in this lecture. For black hole mechanics, all we need is a weakly oscillator horizon. So we need that this omega has to be preserved. Okay, so let's now go to the first law. So again, as Eric Gorgolon must have presented to you, so you have this standard formulation. And what is normally done is you take, let's say, a curved black hole or a Schwarzschild black hole. You can, of course, extend it also to other matter fields. You have, first of all, the ADM mass, which is the full mass of the space-time in that situation. So that is m. You define surface gravity by the acceleration of your time translation vector field. You have the area of the horizon. You could, of course, have electric charges. You could have the electric potential under charge. Here, I'll just talk about angular velocity and the angular momentum. So in this case, the J would be the angular momentum at infinity, so including the whole space-time, and omega is the angular velocity of the time translation killing vector field at the horizon. Okay. So this is what is usually in the standard formulation, the first law of black hole mechanics. So you should notice here that the quantities, which is m, is the ADM mass, so it refers to infinity. The surface gravity, it refers to infinity in the sense that you need the killing vector to be normalized at infinity. Okay, so it's unit time translation at infinity, and that is what leads you to a specific value at the horizon. Similarly, the angular momentum is defined at infinity, it is an integral at the sphere at infinity. On the other hand, the area and the angular velocity are measured at the horizon. Okay. So as presented here, it is a mixture of things happening at the horizon and including also infinity. So it's natural to ask the question, well, how is it then that if I have a black hole in a dynamical space-time, then I don't want to refer, in fact, to infinity at all. So I may not even have access to infinity in certain situations. So I only have access to the horizon itself. Can we reformulate this first law in such a way that everything is local to the horizon? So this should then work also for a black hole, even if it is immersed in a dynamical universe, right? And of course, we still have the condition that there's no infalling radiation, but this is, there are many cases where this doesn't happen. So, the physical content is quite non-trivial. So it must be that in these situations, can we define for black hole mechanics for such a situation. Okay, so this is the motivation. So in fact, if you have questions, then this is a good time to ask it for the motivation, right? Because now we'll get into some technical calculations, but as far as the motivation is concerned, you should ask questions now.
Questions, please. I don't see any at this stage, but.
Okay, good. So let's go on. So I will need for this calculation, I won't present all the details here. I'll just present the summary of the results and the basic idea of the calculation. So we need to know at least some basic things about Hamiltonian mechanics. Okay. So our calculation will require us to define suitably energy and angular momentum of a horizon. And this will be based on a Hamiltonian calculation within GR. So let us briefly discuss this in sort of a very familiar context to students, which would be phase space and classical mechanics, okay? So imagine that you have canonical momenta P, and then you have the coordinates Q, and you have the Hamilton's equations. So I'm given a Hamiltonian function on phase space. So then this tells you how, starting from a given point, how that point evolves in time, okay? So if you wish, this equation defines then a flow on phase space in the standard way. So I will just reformulate this in a slightly different way. So you define what is called a symplectic form. So this is this canonical form of this is omega, which is written as this wedge product between dq and dp. And this is meant to be, can make this very general, this is meant to be a non-degenerate closed to form on your phase space. Then for any Hamiltonian h, so any function h that you wish to interpret as, to use it for time evolution, so you can interpret as a flow of a particular vector field, and it's called the Hamiltonian vector field for h, which is defined in this way. So xh is defined such that if I contract xh with omega, that should be the differential of h, okay? So with this form of omega and then and with expanding dh, you can easily show that this xh must be given by this expression here. Okay. So in other words, given any function, I can define its Hamiltonian vector field in this way. And this is what is telling you the flow in phase space. Okay. So let's now apply this in our case. So now when you talk about phase space in gravity, so you might, I mean, for people who will be familiar with these calculations, you might think of the canonical formulation of GR. And in fact, that is true, so you can do that, but that is quite complicated, right? So you have constraints and a bunch of other things. And it's not an easy thing to work with. On the other hand, there is a different formulation of phase space for GR, which is in fact, you don't need to do a Legendre transform, you can work with the Lagrangian itself. So, and this is known as a covariant phase space formulation. Okay, this is maybe not as familiar to students as it should be, but in fact, it has been developed quite extensively by a number of people in the last, I don't know, 30, 40 years, I would say. And there's many important results, especially by Bob Wald on the situations. And this is following this approach here, okay? So the phase space now is a solution to the classical field equations with the suitable boundary conditions. So I take the classical field equation that is obtained by extremizing the action, and that is then the space of solutions that you look at, and that is your phase space, okay? So we require now that these boundary conditions have to be respected. So in other words, we must require that we have fall off conditions at infinity. So this is meant to be a part of space-time to which we apply this. So we have the inner boundary, that is your horizon. We have the cylinder space like infinity. So that is this tau infinity here. We have an initial time surface and a last time surface here. So we look at this portion of space-time, and we have the field equations there. We can include other matter fields if you wish, and that the formalism goes through completely. And yeah, so then it's a space of solutions, and and we shall, this is then our phase space, okay? So it is, and again, you can do this calculation in different formalisms. The easiest one is in fact a first order formulation. So in this case, you take the fields to be a tetrad at each point of space-time, so that is EA. This index I tells you that there are 4 tetrads, 4 basis vectors here, kind of higher dimensions. So this I is an internal index, if you wish. And there's a connection connected to that. So this is the connection AA with this index IJ. And the curvature of this connection is F. Okay, so it's a first order formulation of GR. And it turns out that you can write action in this case in this particular way. Again, I won't go into details here. I just want to give you the idea of calculation. So the action can be written as the contraction of these internal indices of a quantity sigma and the curvature F of this connection A. The sigma is just a combination of the tetrad. So it is this, it includes this wedge product here and the dual in the internal space. And this integrates over the whole bulk. There's a boundary term that appears at infinity, and there'll be other terms that appear if you have other matter fields. Okay, I'm not going to mention that here at the moment. And I won't even tell you what this boundary term is, but it's a very standard boundary term. So now, this again, there's a machinery that you can apply in this case by looking at variations of the action, by looking at second variations, that gives you the symplectic structure. But before that, you have to know that this action principle is well defined without any additional boundary terms at the horizon, okay? So we have this boundary term, this is well known, at infinity. Then the question is, do we need an extra term at the horizon? Yes or no? And it turns out that, in fact, for a weakly oscillated horizon in which you have constant surface gravity, you do not need any extra term, okay? So the validity of the action principle is guaranteed, in fact, as a consequence of the zeroth law that we've just shown. Okay, so that is the first interesting fact in this formalism here. Now there's a standard procedure, there's a crank you can turn by looking at various second variations of the action, and that gives you a symplectic structure in this space, in this phase space here. So it's now a very much more complicated space than our finite dimensional classical mechanics example. It's an infinite dimensional space of fields in this with this satisfying these boundary conditions, but still there's a well-defined symplectic structure. So therefore, given 2 variations of your of the solutions, so let's call them delta 1 and delta 2, which would be solutions of the linearized field equations, then you can use a symplectic structure and get, which is called omega, can apply that to these 2 variations and get a scalar at the end of it. And just as a technical term, this is written as an integral over any spatial surface in this of this form, but it could be any integral. It's not, it should not be taken to be the standard canonical formulation. Okay, so it's really covariant formulation for phase space here. And then you can ask the question now, well, let us look at time translation, let's look at angular translations, and let's try to find the Hamiltonian which generates these time translations. So exactly in the same way like we did in standard classical mechanics. So just like we have for any Hamiltonian, you will have a certain Hamiltonian vector field, and that gives you a flow in phase space. So similarly, you can ask, well, is the opposite question. So we have a flow in phase space determined by time translation or by rotations. Is there a Hamiltonian corresponding to these transformations? And that will be the heart of the calculation that we need to do here. Okay. So for example, you can look at time translations that effectively means that you take the lead derivatives of the tetrad and the connection, and then that gives you the this general variation. And then you ask the question, well, given the symplectic structure, given this time translation variation here, is there a Hamiltonian which satisfies this equation? So is there a flow in phase space given by Hamiltonian which generates for you these transformations? In a similar way, you can ask yourself, if I look for rotations now, not time translations, so in this case, the transformations would be the lead derivative in the phi direction of your tetrad and your connection. So then you can ask yourself, is there a Hamiltonian that generates these transformations in phase space? And if you remember again your classical mechanics, this should remind you that this is how you define conserved quantities in classical mechanics, right? So angular momentum is what generates rotations and energy is what generates time translations. So it's exactly the same framework here. Okay. So now there's one more fact, which again you have to know, which is that in our case, since the whole theory is diffeomorphism invariant, the Hamiltonians that we get by these calculations turn out to be exactly surface terms. There is no contribution from the bulk. Okay. So for example, if you look at the translations of along with generate rotations, so you can do that calculation and it's, it's not that complicated. It turns out that the Hamiltonian has then two surface terms, one term at the horizon and one term at infinity. Okay. The term at infinity is the standard ADM angular momentum at spatial infinity. So similarly, in this calculation, then you identify the term at the horizon by the horizon angular momentum. So this is then sort of the, the Hamiltonian way to define what we mean by the angular momentum of a weakly oscillator horizon. Okay. And in a similar way, if you apply this to time translations, you get the energy of the horizon. Okay. So there's a bunch of concepts here, which a lot of which I don't have time to go into detail here, but I hope that at least the idea was clear, concepts were clear. So it's perhaps a good time for questions if you have any.
Any questions? I don't see any, but.
Okay, so either this was completely clear or completely unclear. I don't know which one it was. I hope it was completely clear.
Students, can you kindly respond? It'll be helpful, if you have questions or require clarifications, if you can state them so that Professor Krishnan can get back. Are there any questions, comments? Okay, there are no comments or questions.
Okay, so let's then proceed, and I hope that it becomes clear as we go along. So let's first do this procedure for the angular momentum. Okay. So what you do then is that you say, well, let us fix a symmetry at the horizon. So then we have a rotational symmetry of the horizon, that is this quantity vector field phi a, and I fix a rotational symmetry at infinity. Okay, so that is phi a at infinity. Okay, and this is a sphere at infinity. So now in the bulk, let's say that this phi, not the var phi, but this normal phi, is then a rotational symmetry in the whole bulk, such that at the horizon it becomes this phi, and at infinity it becomes this phi infinity. Okay. So then I can transform this any solution, apply this rotation to any solution, and then I can compute the Hamiltonian for this solution, for this rotation, right? And that Hamiltonian turns out to have this particular form here. So first of all, you notice that this quantity here turns out to be variation of a quantity at the horizon. It's an integral at the horizon. So it's the angular component of this omega. And then I have a second term at infinity, which is the standard ADM angular momentum. Okay. So this is how you derive the ADM angular momentum in this formulation. So this expression that we get then for the horizon angular momentum is on the same status as the ADM angular momentum. Okay. So this is what you should say is the spin of the black hole. So I take this one from omega, take its angular component here, integrate that over the horizon cross section, and with the prefactor, that gives me the angular momentum. Okay. And this combination is then guaranteed to be the Hamiltonian, which generates rotations in the whole spacetime. Okay, so this is then the clearest definition of angular momentum for a weakly oscillator horizon. Then let us do a time translation, which will be more interesting. So now look at time translations along a vector field T, okay? So at infinity, again, following the same procedure like before, this should approach a fixed time translation at infinity. So we can choose it to be as you like, okay? It doesn't really matter. At the horizon, this should be a symmetry vector. So let's assume that the horizon is still axisymmetric. So there is a rotational symmetry phi at the horizon. Then we require that just like in a Kerr solution, right? So this T must be a combination of L and phi. So let us then require that this T should be some B times L times omega times phi. On a given space, on a given solution, the B and omega are constants. However, these B and omega are not constant over phase space. So these can depend upon the infinite dimensional phase space point that you're at. Okay, so this is saying that the time translation can be made to adapt to different horizons as required. Okay, so what this dependence should be will be given by the calculation of the Hamiltonian. And in fact, you can calculate now this quantity here of this symplectic structure of any variation and this particular time translation. And this is then the result. So once again, you have two combinations. You have terms at the horizon and terms at infinity. So the term at infinity is this one, which is then the ADM energy corresponding to that time translation that you've chosen. And you get terms at the horizon. You get a term including angular momentum multiplying by omega, which is still a free thing at this moment. And you get another prefactor here, which multiplies the variation of the area, which is again defined at the horizon. And this kappa is just this B times L dot omega. So this is the surface gravity associated to this vector field T at the horizon. And this omega is angular velocity connected to that vector field T at the horizon. Okay? And unlike in the standard formulation, the J that you get is the local angular momentum of the horizon. It doesn't refer to the ADM angular momentum, right? But we saw this is the same status as the ADM angular momentum, but it is computed locally at the horizon. Okay? So therefore, then you say, well, the energy of the horizon corresponding to this time translation, let's call it ET, variation of that should be given by this expression here. And so far, this kappa T and this omega T are free. So these on any space-time are a constant, but these can depend upon, it's a function in phase space. Okay? So this is sort of, very interesting, right? So the first thing you notice is that, well, if I take kappa and omega to be very complicated function of phase space, it's an infinite dimensional phase space, right? So in this phase space will be black hole horizons, which are highly distorted, which could be spinning and will have, high multiple spin multiple moments and so on and so forth. If I require kappa and omega to depend upon these extra parameters, then I cannot integrate this and get the energy. In other words, the Hamiltonian is not guaranteed to exist for any choice of kappa and omega. So in order for the energy for the Hamiltonian to exist, I must be able to integrate this equation. In other words, it must be so that this kappa and omega satisfy this integrability condition. So therefore, it must be that this kappa and omega are functions only of A and J. So of all the translation vectors I could have chosen, I can't choose the B and omega to be as I like. These must be functions only of A and omega. And in fact, they must be functions such that this integrability condition is satisfied. So once you do that, then in fact, there is Hamiltonian that exists in phase space, which generates time translations. So in this framework then, and this is the first law for this time translation. So the first law of black hole mechanics in this framework is a condition of the existence of Hamiltonian in phase space, which generates time translations. Okay, so this is radically different interpretation of the first law that appears here, which you do not have in the standard formulation. And of course, it is completely local. So it depends only on the area and on the angular momentum defined at the horizon and defined through this Hamiltonian calculation. Okay, so again, good time for questions. Any doubts, any comments here?
Students, comments, questions? Yeah, there's one hand among them. Guillaume, please go ahead. Please unmute and speak, Guillaume.
Yes, I hope you can hear me.
Yes.
Yes, we can.
Okay, very good. Yes, I have two related questions. I want to be sure I understood. So the variation you were talking about, delta, it is always among solutions of the field's equation. Is that correct?
Yeah, so these are solutions of linearized field equations, yes.
And the linearized field equation, exactly, okay. And then I don't know if it's really a question, but it seems that in fact it's not really a proof of the first law. It's more restatement. So the question is now whether there exists such a suitable Hamiltonian.
Yeah.
So it's more a comment, but or you can maybe comment more about that.
Well, it is true. So you're completely right. So of course it is a restatement, but at least to us, it clarified the role of the first law in this Hamiltonian setting. But it is, you're right. So it is not a proof. It is telling you, what has to be satisfied such that the first law holds, such that a first law holds, for example.
Thank you.
Thanks, Guillaume. Are there any other questions? Yeah, there is. Srijit, did you have a question? Srijit, there is someone had raised the hand, but did anyone have a question? Okay, there are no other questions at this stage.
Okay, so let's go on. So now, as I said, there's an infinite number of choices you could still make for permissible time translations in phase space. So by permissible now, I mean all the t's for which a first law holds, for which Hamiltonian exists. Okay. So the procedure is one way is the following. You choose a function kappa of a and j. And then, so you use kappa, and then you integrate this omega as a function of a and j from this integrability condition. And then the kappa and omega that you get, you plug that in here, and that gives you the energy. Okay. So now, again, this is a choice that you can make, and this is then motivated by the uniqueness theorems. So if you want to single out, let's say in your space of solutions, I mean, you're free to do this, right? So if you have a special space of special set of solutions within your huge phase space, you can sort of tailor your choice of time translation connected to that subspace of solutions. And in this case, we have the Kerr solution, which are privileged in this class I'm looking at. So if you had to include electromagnetic fields, then you could of course, have the Kerr-Newman solutions and so on and so forth. So then you have a choice you can make of kappa, which is exactly the same dependence on a and j as in Kerr. So this r here is just the radius of the horizon. That's area upon 4 pi in the square root. So I just require that kappa has to be this. And then I integrate the equation, then I get omega to be exactly, of course, as in Kerr. And then I get a privileged energy of the horizon, which then can be called the mass of the horizon. So there's, of course, other conditions that this has to be satisfied so that I can call this the mass. So for example, I can ask the question, well, is this connected to sort of the flux of energy at infinity? And that is true. So if I take my initial data slice and I say that I have the ADM mass at infinity and I have the energy at the horizon, so the difference then must be the energy that is radiated at null infinity. And that is the case with this mass definition here. Okay. So now what have you achieved by all of these calculations, right? Might seem abstract and so on, but what you've achieved are two things in a sense, right? First, you have obtained expressions for the angular momentum and the mass of a black hole, which is defined purely locally at the horizon. And this you can apply in many different situations. You can apply this in numerical relativity, which is what I'll talk about in tomorrow's lecture. And this is really well suited for that purpose. Of course, you have to deal with then things which are not isolated and so on, but yes, and one can do that. But this gives you sort of a framework for applying these calculations in a physical situation, okay? And secondly, you achieve that you can show the black hole laws of black hole mechanics, the zeroth law and the first laws, all formulated locally at the horizon, with no reference to things at infinity here, okay? So this is, if you like, the basis, the underlying reason why we can apply this expression for the angular momentum, which is done, all the time in numerical simulations. Why can you apply this, and why can you call that result the spin of the black hole?
Badri, there is a question in the chat. Srijit asked what kind of boundary one may include in this IH setup. Boundary simplex structure. Is the boundary symplectic structure unique?
Yes, so it is unique. So, well, I should say that there's things with gauge transformation that one should be careful here, because if you just apply these naively, then you have directions in phase space along which you can go and not change in the symplectic structure. So that's why it's then a degenerate symplectic structure, if you wish. So modulo that, if you take care of that, so it's a pre-symplectic structure. But if you sort of take care of that, then yeah, so then you do get terms at the boundary, and then it is all well defined. Yes, it is the case. So the symplectic current that you get from which you compute this omega, that is a closed one form in phase space. So therefore, it is well defined.
Trust that is fine, Srijit. There are no other questions at this stage. Yeah, Srijit says thanks.
Okay, good. So then I hope that you at least appreciate then that this definitions of J of angular momentum for the black hole and is at the same status as the ADM angular momentum. And okay, the mass is a little bit different. You need this extra argument to get the mass, but at least it is within the same framework. And if you make this choice, you're guaranteed to have a permissible time translation which generates, which is given by Hamiltonian in phase space. Okay, good. So now let us change gears a bit. So far we have obtained the mass and the spin of a black hole, well, of a weakly oscillating horizon. And I should say that it is straightforward to include matter fields. So you can include electromagnetic fields, Yang-Mills fields, dilaton fields, and so on. And again, you get, well, there's certain complications when you don't have this unique sort of Kerr solutions in your phase space, when it's more complicated. So then you have to work a bit more, but still the framework still holds. Okay, you can get interesting information for black holes and Yang-Mills fields in this formalism. But of course, the black holes themselves are not, the geometry is not fully defined by the mass and the spin just, right? So let's now restrict ourselves again to vacuum spacetimes. So the black holes can be distorted. So you can have higher multiple moments. So you can have matter field that surround the black hole. You can have a binary companion and so on and so forth. So it is not the case that just the mass and the spin determine for you the full geometry of the horizon. Okay? And in many instances, the black hole itself can be to a very good approximation, and over a short enough time scale, it can be approximated extremely well as an isolated, as to be isolated. So in this case, the black hole is still isolated. It is very different from Kerr possibly. It can have many distortions. And then you want to ask the questions, well, can this formalism be used to obtain what we might call as multiple moments for the black hole? Okay. So of course, you have the field at infinity, right? So there is a well-developed formalism for extracting the multiple moments at infinity. So you take the gravitational field at infinity, expand that in suitable spherical harmonics, and then you have what you might call the field multiple moments at infinity. Okay. But you want to now here compute the source multiple moments as well. And the two things are not guaranteed to be, they are not the same, in fact, in GR. So within Newtonian gravity, within Maxwell theory in flat space, it is the case that there's a very close relation. They're the same if you take moments of the source or of the field, right? So they are closely connected. This is a much more difficult question in GR. So the two things are not the same. And it's very interesting to investigate the relation between the multiple moments at infinity and the multiple moments at the source, right? And to do this, we need, first of all, a good definition of what we mean by source multiple moments. And so this for weakly oscillator horizon. Okay. So now recall, as we discussed now numerous times so far, that the geometry of the horizon is determined by two things. One is the degenerate metric, Q, and this one from omega. Okay. And we shall restrict ourselves now to axially symmetric horizons. So then, therefore, we have a symmetry phi that preserves both Q and omega. Okay. So then in this setup, then the question is, how do we extract a set of multiple moments, by which I mean a set of numbers from which I can reconstruct the geometry given by the Q and the omega? Okay, so that is the question. How from this do I get multiple moments which can be used to describe this geometry? So let's do that. So the way it is done in a standard let's say in Newtonian gravity or in for a charge or a mass distribution is to decompose things using spherical harmonics, right? So for example, you have a mass distribution, you could decompose that in terms of spherical harmonics, or you have a surface charge distribution, you can again decompose it in terms of spherical harmonics. If you have vector or tensor fields, and there are sort of extensions of these for those situations. So then we have two questions here. So first of all, at a black hole horizon, so imagine now there's a weakly oscillator horizon. So we have some theta and phi. So which theta and phi should we actually use? Because I can use any theta and phi here, right? So in GR, I can change coordinates. I'm not privileged to use one particular theta and phi. I can make a transformation and I get a different one. And if it is not privileged in any way, then that's also fine. So, and if I take the YLMs in both of these different coordinates, I will get very, very different numbers. Okay. And the second question is, which fields should I decompose, in fact, at the horizon? Well, we said it was Q and omega, but can we say a bit more? Can we say, you know, some more easily visual fields that we can easily visualize? Okay. So in fact, for the case of axisymmetric horizons, there is a very nice formalism where you can do this, so which is what I will describe now. Okay. So the first thing is to now define for you a coordinate system theta and phi in which I will decompose the different fields. Okay. And this should be connected to the axial symmetry that we have. So we have the symmetry phi, and then I require then that this coordinate phi should be the parameter along this, should be along the integral curves of this axial vector field. So I require that this, for example, that this vector field phi should have 2 points where it vanishes. So these are the 2 poles of the horizon. And I can then choose this coordinate phi to have the range from 0 to 2 pi always. Okay. So this defines, so given a vector field phi, this defines for the coordinate phi over the whole horizon, and the range is as we expect from 0 to 2 pi. So now we need the analog of the coordinate theta, which should be orthogonal to phi. So how do we do that? So first of all, as I said, we assume that this phi has closed orbits and it vanishes exactly at 2 points, which are the poles. The other coordinate z, which we call zeta, which is connected to theta, right, which is analog of cosine theta, in fact, is defined by these two relations here. So the first one is that I take the volume element on the sphere. I take the dual of this phi, if you wish, by contracting that with this epsilon. And that is meant to determine for me this coordinate zeta, which is the analog of cosine of theta. So this definition itself does not fix for you a constant, right? So I can add to zeta any constant, and this is still satisfied. So I require then that I fix a constant by requiring that the integral of zeta is vanishing over the whole horizon. So on the northern hemisphere, it is positive, southern hemisphere, it's negative, right? That's the so that's the condition here, which is singled out by this here. So now from the definition of zeta, it's clear that if I contract d zeta with phi, so then contracting this epsilon with phi twice, so that is 0 because it's antisymmetric. So therefore, this vector field psi a, which is just dA zeta of the index raised upstairs, is then orthogonal to phi. Okay, so this gives me then two orthogonal direction on the sphere, and therefore then you can show, in fact, that the metric on the sphere can be written in this form. Can be written as overall factor, that is r square, that is given by the area. So 4 pi r square should be the area of the horizon, and that there should be only a d zeta square and d phi square. The cross term vanishes because it's orthogonal. And moreover, the function that appears here are only functions of zeta because nothing depends upon phi. And finally, and very importantly, these are inverse of each other. So I have an F inverse here and an F that appears here. Okay. So for example, for a round sphere, if you take the zeta to be cosine of theta, then this is completely true, right? You can just check that this is given by the metric where F is just 1 minus zeta squared. So 1 minus zeta squared is 1 minus cosine square of theta, so that is sine square of theta. So then we get sine squared theta here, and then you can just check that if you just do this little differential, then you get the exact, the metric on the round sphere as you expect. Okay. But this is a nice generalization of the whole formalism in which you have these functions appearing exactly in this way, and they're functions only of this quantity zeta. And even more, which is even more nice, which is that the scalar curvature of this metric is given by the second derivative of this f. So it's given by 1 upon r squared times f double prime of zeta. Okay. So this structure is given to you anytime that you have a symmetry phi, you can construct these coordinates and then you have this metric in this form given to you. Okay. So therefore we shall take this zeta and this phi to be the privileged coordinates on the sphere. I can always, given any sphere which is axisymmetric, I can go to these coordinates and write the metric exactly in this form. And then what we want to do, we want to expand then suitable fields on the horizon. And in this case, in fact, these turn out to be, as I'll argue, these turn out to be the scalar curvature of the horizon and the dual of this differential of omega. So these are the two fields that we should use. And the decompositions of these in terms of the Legendre polynomials, in this case axisymmetric, so I just have the m equal to 0 multiple moments. That's why I have the Pn and not YLN, right? So these then give me the mass and the spin multiple moments of the horizon. Okay, and these are in fact different from the moments we define from the field moments at infinity. Okay, and the difference between them is a very interesting question, which is not fully understood yet, about how it is that, the relation between both of these things, depending upon the different physical situation that we are in. Okay. So, well, the other thing that I will say is that, well, why is it specifically this scalar curvature and this d omega? The first thing is that, well, the scalar curvature appears because given the scalar curvature, I can back and get my f, and therefore then the metric, right? So given r, I get the metric in this form, exactly. So the scalar curvature gives me the metric. So that is the first thing. And the other part of the geometry was this omega. And in fact, given this Jn, you can show that this omega can also be reconstructed in this way. And finally, we recall already from last time that if I now go back to what we discussed very early on, which is that this differential of omega gave me the imaginary part of psi 2. The real part of psi 2, in fact, gave you the scalar curvature. Okay? So therefore, what we're actually doing is we're decomposing psi 2 at the horizon. This very special wild tensor component is what gives you the horizon multiple moments. Okay? So for the Kerr black hole, you can calculate what these moments are, and they're different from what you get at infinity, right? And they have different purposes, right? So the one at infinity is the one that is often more relevant for the equations of motion, but there can be many situations where in fact these source multiple moments are very important as well. And this gives you a nice way to define and calculate these multiple moments. So then I'll stop here. So the next step in tomorrow's lecture, I'll talk about time-dependent situations. I'll talk about the second law of black hole mechanics, the area increase law, and applications to numerical simulations. So then I'll stop here, and we have still 5 minutes or so. So I'm happy to take more questions.
Thank you, Badri. Questions for Professor Krishnan, please. Are there any questions/comments? Do you like him to clarify any point? Yeah, Sumit, unmute and speak, please.
Am I audible, sir?
Yes.
So in this first order formalism, you actually, I mean, you did not show the boundary contributions, but I mean, my question is like, I mean, in this, I mean, the boundary contributions, I mean, from the first order formalism and the second order formalism, are they kind of equivalent in the sense?
Yeah, that's a good question. So they're not equivalent, in fact, and I think this is maybe underappreciated fact, which is that in this covariant phase space formulation, it is not guaranteed to give you results from the first or second order formulations. Okay, so it's not, they turn out to be the same. In fact, I presented for you here the calculation. Well, I've summarized for the calculation in terms of this first order formulation. There also exist formulations of the same calculation in the second order case. There's something maybe more familiar to most physicists, and you get the same result, but you do get different boundary contributions in that case at the horizon. So in this case, what happens is that there turn out to be no additional contributions at the horizon. And that is guaranteed, in fact, by the zeroth law. And this is not the case in the second order formulation. So it wasn't guaranteed, I think, in this covariant phase space formulation that you should have gotten the same results, but you do. So which is reassuring. So you don't expect to get different results from these calculations, and that is the case.
Thank you.
You have further remarks, Sumit?
No, thank you, sir.
Yeah, thank you, Sumit. Chandra, you have a question?
So this higher order multipolar structure of the field, was it in context of was it in a non-GR context, or like I was wondering for isolated black holes, they shouldn't exist in GR thing, right? Or did I miss a point?
Why do you say they shouldn't exist?
Like for Kerr, shouldn't we assume that it's purely quadrupolar?
No. So it's not quadrupolar, in fact. So I mean, you have non-vanishing moments at high L's also. I mean, there's a very simple formula for the field moments, which are the Gaussian moments, and it's not that they are quadrupolar. So you have the higher moments as well. And in fact, you do this for the curve horizon, you can calculate this and you get very specific expressions of the mass and the spin for the higher moments. So they don't vanish, but what is true is that for Kerr, the mass and the spin determine all the higher moments.
Okay. Okay.
But it is not true that it is purely quadrupolar.
Okay. Okay. Thanks. Thanks. Yeah.
And that is the same feature whether you have the moments at infinity or at the horizon. So you do have the higher moments, but they're all determined by just these two numbers, which is a very non-trivial thing, which is not true for a star or other matter distributions, but it is true for black holes.
Okay. Okay. Thanks. Thanks. Yeah.
Thank you. Are there any further questions? Okay, I don't see any further questions, Badri. So let me thank you for your lecture today. Oh, I'm sorry, there is one more. Sumit, yes.
Yeah, sorry, I got a bit late. I mean,
No issues.
good. I mean, can you suggest some references for this covariant phase space formalism, if it is possible?
Yes, I can. So I can add the references to the. So the standard references are. Let me just go back here. There's a nice paper by. Well, there's very nice lectures by Witten, which not that easy to find, I think. But there's a article by, I don't know how to pronounce this, Shinkovich, and there's a very important paper by Wald and Zupas. So these are sort of the standard references. There's also notes by Ashtekar and Bombelli. So I can give you specific references here, so with the journal name and so on. But these are the references.
That will be very helpful. Thank you.
Thank you. Any further questions? If there are no further questions, let's thank Professor Badri Krishnan for his lecture. Thank you, Badri, for your lecture. We hope to see you all, we hope to see you tomorrow at the same time. As far as today's program is concerned, I think we have a couple of hours break, and then our next lecture will be by Professor Eric Poisson at 17:30 Indian time. Thank you very much, and we'll see you all in a couple of hours. Thank you, Badri, for your talk. Bye.